Welcome back. I initially planned to tackle another Flutter feature in this video, but there's this lingering encryption layer rewrite I've been putting off for way too long, and it's actually starting to delay other things. So it's time to finally rip the band-aid off. But obviously, before we start writing code, how does Manitou current encryption layer actually work? Well, first, the user creates a pin. This pin is fed into our encryption utility, which utilizes libsodium under the hood. Inside the utility, we derive a key using argon2id. And then, things get a bit weird. We generate a random ciphertext, feed those random bytes into the database initialization to act as the password, and then encrypt that ciphertext using the derived key. If you're paying attention, you might be thinking, we already have argon2 key derivation. Why are we doing this extra encryption step?
I don't know.
Honestly, I wish I could ask past me what the logic was there. It's technical debt, and today we are paying it off. The new encryption layer is going to be vastly simpler. We derive the key from the user pin and right away use the derived key directly as the database password without any more unnecessary random byte iteration. So let's get into it. First, let's swap this sodium package for the lighter cryptography plus, since we only need key derivation right now. We then install, we start at the setPin function. We generate a salt using secure random bytes, then configure argon2id. For parallelism, I'm planning to cap it at 4 threads, or half the available if it's less than 4. But how? Using Dart IO with it. The rest should follow OAuth's recommendation with a few minor tweaks for extra security. Then I will just reuse the app key storage for the salt for now. Let's make this into derived key function instead, so it could become reusable, and run a quick debug test. Calling toString just prints the class name, which isn't helpful. Let's use the extra bytes instead and call it to base64 for string compatibility. Perfect, 2 attempts resulted in the exact same base64 string. Now for the next part. Okay, so as per the conversion, I was thinking to use the hex format instead because it is lighter, right? Now let's put that derived key to use. We simply update the temporary data store, remove the old encryption block entirely, and return the key directly. Let's give it a go. Alright, seems like everything worked correctly. Now time for the unlocking. First, we fetch the salt. But wait, we can just compare the derived database key because we intentionally never store it. Looking at the old code, the solution is a verification key. We'll store a separate key using the exact same derivation process, strictly for checking the pin only. Let's write a new derivation logic for verification, still using argon2id. Luckily, argon2id has an associate data parameter, so we'll pass in the UTF encoded string verification. Alternatively, you could prefix the plain text pin before deriving. Either way, ensure the same pin produces a completely different hash for verification versus the database key. With the verification key ready, we need a self-compare function. Why? Think of an easy guard who slams the door the instant he spots a wrong letter. An attacker can measure that timing to guess the password character by character. To fix this, we need a throughout guard, a constant time comparison that checks every single letter, regardless of early mistake. The response time is always identical, giving attackers 0 clues. Usually, constant time comparison is built into the languages, except in Dart for some reason. Checking the cryptography plus and the crypto package, nothing. Looks like we have to write our own. Before that though, we need to remove an X appendix added earlier that will break the comparison. Since we saved the key in hex, we also need a hex to bytes helper to convert the string back to bytes. Finally, let's write the verify function. We just need a loop and some bitwise operators. This code acts as a difference collector. The XOR operator compares characters returning 0 or a match and non-zero for a mismatch. The OR assign operator acts as a sticky switch. Once a mismatch is spawned, the result stays non-zero until the very end. Let's visualize how this difference collector actually works under the hood. Imagine our correct pin is 7294, but the input gas is 7214. We start our result variably 0. As the loop checks the first 2 digits, the XOR operator sees the match perfectly and inputs 0. 0 are assigned with 0 stays 0. So far, so good. But on the third digit, a 9 versus 1, XOR spots the mismatch and outputs a non-zero number. This is where our R assign operator acts as a sticky switch. It absorbs that non-zero number, meaning our result is not permanently altered. And here's the crucial part. Even though we already know the pin is wrong, there is no early exit. The loop is forced to keep going and check the final digit anyway. By the end, our result isn't 0, so the pin is rejected because we didn't break early. The time it took to reject a class guess is exactly the same as a completely wrong guess. Safe and sound. Now let's give check pin a try. Because we simplified the logic, the pin circuit does not need encryption utility anymore, which used to require asynchronous initialization. So now we can strip out the async logic entirely. Let's make the change. Next up, let's revise the onboarding configuration. Right now, the logic is scattered, so we're going to tidy it up using refactor new experimental feature. Honestly, figuring out the right way to use mutation was a bit confusing. Tried different patterns like this, and this before eventually settling on a local mutation. It does push the logic into the fill layer, but gets the job done. Time to give it a try. We run through the setup and nothing happens. Completely stuck. Looking at the diffs, we completely forgot to write the direct logic. That explains it. With the redirect edit, let's test it one more time, and perfect. Now it works. This refactor has taken a bit of time. If things look different, it's because I just moved to Hyperland. Tiling window manager are just perfect for this kind of workflow, you know? Anyway, let's get back to it. It's time to refactor the change pin flow to use our new key derivation logic. First, we create the refactor mutation, and then we adjust the view to consume it. We're also going to use a custom run callback utility here. It lets us handle success and error states via callback while guaranteeing the widget is still mounted. That means we can finally say goodbye to scattering if context mounted text everywhere in our UI. There might be a tiny bit of overhead with this approach, but for this use case, the cleaner code worth it. Let's move the rest of this execution code down into the unsuccessful. And that's it. Now we'll just quickly apply the exact same pattern to the check pin sheet, since it does a very similar job. Alright, next up we are fixing the change pin flow to use our new system. The change here should be minimal since we're just calling the updated service, so we just need to update the wiki function. Because we are not explicitly returning the derived pin anymore, we just patch it directly from the temporary store since setPin service handles setting it. It feels a little fragile, but let's run and see if it's working. Spoiler alert, it didn't go well. Upon inspection, the app completely failed to open the database. The culprit seems to be because we were passing the raw alt pin instead of the derived one. A quick fix to pass the derived alt pin instead, and perfect. The change pin flow is officially working again.
And that's it for the pin refactor. Next time we will tackle the biometric authentication. See you then.